Swayam Prabha. Digital India. Educated India.
We shall now discuss what is meant by ventilation perfusion matching and what VQ mismatch is. We have seen earlier that alveolar ventilation is 4.2 liters per minute and perfusion or cardiac output is 5 liters per minute, the amount of blood that goes into the lungs every minute. How did we get this number? If we breathe in 500 ml with every breath, 150 ml of that is held in the anatomical dead space, which is the trachea and the bronchi. This does not participate in gas exchange. Therefore, the volume that reaches the alveolus and participates in gas exchange is 350 ml, which is 500 minus 150. And if there are 12 breaths per minute, we get an alveolar ventilation rate of 4.2 liters per minute. What we have considered here are total ventilation and total perfusion. The concept that we shall discuss now is that for effective diffusion or effective gas transfer across the membrane, particularly oxygen transfer, it is ideal to have equal ventilation and perfusion. Not just overall ventilation and perfusion, but ventilation and perfusion at every alveolar unit. If you have a certain volume of ventilation, it's ideal to have the same volume for perfusion. Or if the V by Q or ventilation perfusion ratio is 1, that is where the best oxygen transfer occurs. When we discuss VQ matching and mismatch, what we shall see is that even if total ventilation is normal and total perfusion is normal, there can be regional mismatches of ventilation and perfusion, and that amounts to diffusion impairment. It affects oxygen transfer alone and not carbon dioxide transfer. That is the message in this lecture. In this case, the overall VQ ratio or the total ventilation perfusion ratio is 4.2 by 5, which is about 0.8. Remember, we've seen that respiratory quotient is 0.8 earlier, that is purely incidental. VQ ratio is also 0.8. For ideal gas exchange, it's good to have a VQ ratio of 1, not just total VQ ratio, but regional VQ ratios. Take a look at this image. This image is adapted from a textbook called Pulmonary Physiology by Levitsky. If this is the end expiratory status of the lung, what can you comment on the volume of air and the volume of blood in this image? All the white spaces within the alveoli represent the air held in the lung, and whatever is in black is in the alveolar walls, the septa, and represents the blood that is there in the alveolar walls. Draw your conclusions about the amount of air held and amount of blood held in the lungs in the end expiratory state, end of normal expiration. That is when the lung is at the functional residual capacity. So the logical conclusion would be that there is more air in the apices of the lung and more blood in the base of the lung. Can we extrapolate this to ventilation and perfusion? Can we say that ventilation is more in the apices and perfusion is more in the basis of the lung? That would be an incorrect statement, and we shall see why just now. So this is an interpretation of what we have seen here. At the end of normal expiration, the alveolar volume in the apex of the lung is more than the alveolar volume in the base. The reason for this is that the negative pressure in the pleural space in the apex is more than the negative pressure in the base. Therefore, there is a suction effect holding the alveoli at an expanded volume in the apices of the lung than in the base of the lung. We shall see that in greater detail later. But now if this is the situation, at the end of expiration, when you take a fresh volume of air, when you breathe in tidal volume, where do you think the new air will go? Here is a balloon that is partially expanded already and therefore is more tense than this less expanded balloon. Obviously, this less expanded balloon is more compliant and the new air will preferentially go into the base than the apex. Therefore, ventilation, which is actually the amount of new air that enters the lung, is also more at the base than the apex. The impression you drew about blood supply to the lung is actually correct from this figure itself. Perfusion is more at the base. And what we understand from this cartoon is that ventilation is also more at the base of the lung. Ventilation and perfusion are less in the apex and more in the base of the lung. Let us see how ventilation and perfusion are distributed from the apex to the base of the lung when you are in the standing position. Ventilation is less at the apex and more at the base. This is about 0.24 liters per minute in a reference adult male with a tidal volume of 500 ml. Whereas in the base, ventilation is about 0.82 liters per minute. And if we consider perfusion, again it is less at the apex and more at the base. Those are the values for blood flow through the lungs in the apex and the base. Now if you see, when you consider ventilation in relation to perfusion, there is more ventilation as compared to perfusion in the apex of the lung. And if you take a ratio, V by Q will be more than 1 in the apex. Whereas in the base, there is more perfusion as compared to ventilation. And if you take a ratio of V by Q, it's going to be less than 1 in the base of the lung. So if that represents ventilation and if this represents perfusion, you see that in the apex there is more ventilation in comparison to perfusion, and in the base there is more perfusion compared to ventilation. VQ ratio in the apex of the lung is 3.3 and at the base of the lung is just 0.63. Somewhere along the third rib is where you will get a VQ ratio of 1, where ventilation and perfusion are actually matched. In the apex, we can say that there is some wasted ventilation and we will call that alveolar dead space. In the base, there is some wasted perfusion. If that is alveolar dead space, we call this wasted perfusion physiological shunt. We already know about anatomical dead space, a region where there is no gas exchange, that is the trachea and the bronchi. So alveolar dead space refers to the air that goes into the alveoli, which does not participate in gas exchange because there is not enough blood coming to those regions. So that's what we mean by alveolar dead space. The sum of alveolar and anatomical dead space is referred to as physiological dead space. The summary thus far is that even if the overall VQ ratio is close to 1, we saw it as 0.8, there are regional differences in the VQ ratio even normally. In the apex, ventilation perfusion ratio is more than 1, which means there is wasted ventilation, and in the base, the ratio is less than 1, which means some perfusion does not participate in gas exchange. So in a normal person, such minimal VQ ratio mismatch does not affect oxygen transfer and it is considered to be normal. But in disease states, the mismatch can worsen, and that's what we are going to see now. Now let us consider these 4 alveolar units, and let us say this is the capillaries in the walls of those alveolar units. So this represents ventilation and this represents perfusion. Let us say what you see in purple is the diffusion membrane across which diffusion happens. Ideal VQ ratio on all these alveoli is 1. That is, if you have 1 ml of ventilation, it's good to have 1 ml of perfusion for efficient oxygen transfer. Now, let us say there is some inflammation in the bronchioles of this alveolus. Say there is a mucus plug. So, air is not able to get into this alveolus. Fresh air is not able to get into this alveolus, and whatever oxygen was here would have already diffused into blood. So, that alveolus would reduce in size, or that's what we call collapse. When there is a mucus plug blocking the entry to an alveolus, that alveolus would collapse. This means that there is no gas exchange between this alveolus and the capillaries in the walls of that alveolus. We have lost some surface area of diffusion. But if total ventilation is 5 liters per minute, instead of 4.2, I am just using 5 liters per minute so that we have a total VQ ratio of 1. If total ventilation is normal, that is, if there is no hypoventilation, then the air that did not go into this alveolus will go into other alveoli, and there will be other alveolar units which get more of that ventilation. So, is this going to compensate for the loss of gas exchange in this unit? Not really, because there is only so much blood coming here, and whatever extra ventilation went into this space may not be able to participate in gas exchange. So, here the VQ ratio is 0 because there is 0 ventilation, but in this alveolar unit there is more ventilation as compared to the normal perfusion, and therefore we can say that the VQ ratio is more than 1. Now, let us think of another situation. There is a block to blood flow for this alveolar unit, as would happen in pulmonary embolism, a small embolus blocking the capillary to that alveolar unit alone. Now, this will result in 0 blood supply to that alveolar unit, and therefore there is no gas exchange there. The VQ ratio in this case would be infinity because Q is 0. Now, the blood that did not go into this capillary would now have to go into other capillaries that are there, because we are considering that the total perfusion is normal. Therefore, blood flow to this alveolar unit will increase, but as we saw earlier, this is not going to help compensate for the loss of surface area here, because the amount of air that goes into this alveolus is essentially the same, only the blood flow has increased, and therefore this extra blood flow here is not of any use. If we look at VQ ratio here, we will say it is less than 1. So, in any of these situations, gas transfer or oxygen transfer in particular is non-ideal. The best scenario for effective oxygen transfer is to have a VQ ratio equal to 1. Now, these are the 4 scenarios we have seen here. In this case, VQ ratio is 0. Ideal VQ ratio is 1, here it is 0, and in this case it is less than 1, and therefore we put it somewhere here. So, these cases where the VQ ratio is either 0 or less than 1 are referred to as physiological shunt, where the blood that goes in is actually not participating in gas exchange. There is extra blood going here to an alveolus that is normally ventilated. Here there is normal amount of blood going to an alveolus that is not ventilated at all. So, both these cases where VQ ratio is less than 1 is referred to as physiological shunt. Here VQ ratio is infinity because there is 0 blood flow, and in this case perfusion is less than the amount of ventilation, or VQ ratio is more than 1, not infinity but more than 1. So, these cases where the VQ ratio is more than 1 are referred to as alveolar dead space. The air that went into this alveolus is wasted because there is no blood, or the extra air that went into this alveolus is again wasted because there is only normal amount of blood coming into that alveolar unit. This is alveolar dead space. We are already aware of what anatomical dead space is. Anatomical dead space plus alveolar dead space is what is referred to as physiological dead space. When VQ ratio is less than 1, we know that blood is wasted and doesn't participate in gas exchange. That is referred to as physiological shunt, only to differentiate it from anatomical shunt, as in a reversed extrapulmonary shunt, reversed ASD or VSD, which is also referred to as Eisenmenger's syndrome. In that case, blood is shunted from the right heart to the left heart without going through the lung. And that is an anatomical shunt where the blood does not participate in gas exchange. While this is an anatomical feature, here we are referring to cases where there is a functional shunt. There is blood going in, but it is not able to take part in gas exchange because there is not enough ventilation. And that is why it is called a physiological shunt. It can occur in pathological conditions. It is not all physiological when we say that there is a physiological shunt. We will now consider some interesting corrective mechanisms which attempts to minimize VQ mismatch when there is some local pathology. The best known corrective mechanism is, if there is an alveolus which is collapsed, then there is no oxygen there, the blood that comes here does not get oxygenated. Venous blood will come in with a PO2 of 40 millimeters mercury, and by the time it goes out, we expect it to have reached 100 millimeters mercury. That would not happen because there is no oxygen transfer. There is no new air in this alveolus. So, the situation in this capillary is hypoxia. Hypoxia in this capillary will lead to vasoconstriction of that capillary, a phenomenon called hypoxic vasoconstriction. That happens in an attempt to divert blood to other alveoli which may be better ventilated. So, this is a corrective mechanism which aims to divert blood flow from ill-ventilated alveoli to better ventilated alveoli. And that mechanism, hypoxic vasoconstriction, attempts to reduce VQ mismatch so as to effect better oxygen transfer by matching perfusion to ventilation. There are two concepts we must understand in relation to hypoxic vasoconstriction. Hypoxic vasoconstriction occurs in pulmonary circulation only, whereas in the systemic circulation, if there is hypoxia, let us say an exercising muscle, the capillaries there have less oxygen than usual because the exercising muscle has absorbed all that oxygen. Hypoxia in a systemic capillary will actually lead to vasodilation because the tissues there require more oxygen, and the response is therefore directed towards supplying more oxygen to the exercising tissues. Hypoxia in systemic capillaries leads to vasodilation, whereas in the pulmonary capillaries, hypoxia leads to vasoconstriction. Hypoxic vasoconstriction is a peculiar phenomenon in the pulmonary capillaries only, and the aim of this response is to match ventilation to perfusion. There is a second phenomenon that you should understand with regard to hypoxic vasoconstriction. What happens when there is global hypoxia, as in atmospheric hypoxia? In high altitudes, there is hypoxia in the alveolus, and therefore the arterial oxygen can never go up to 100 millimeters mercury. It can only reach as much as how much there is in the atmosphere and therefore the alveolus. Let us say somebody lives at a certain altitude where the atmospheric PO2 itself is 50 millimeters mercury. Therefore, the oxygen in all the capillaries of that person's lung can only go up to 50 millimeters mercury, or there will be what the lungs understand as hypoxia in that individual. and this can lead to overall hypoxic vasoconstriction, and that will increase pulmonary arterial pressures, leading to a condition called pulmonary hypertension, which can be very dangerous because the right heart has to pump against a higher pressure than normal, and the right heart will eventually fail, leading to cardiac failure. So, in people living at high altitudes, there is a certain prevalence of this phenomenon called pulmonary hypertension, which occurs due to hypoxic vasoconstriction. A normal response which aims to match ventilation and perfusion can create a problem if there is global hypoxia. While hypoxic vasoconstriction attempts to minimize the VQ mismatch in these states, is there a similar mechanism to minimize VQ mismatch in this condition where, let us say, there is a microembolus preventing perfusion to a particular alveolus? Will ventilation to that alveolus reduce? If you're interested, you could read about a possible mechanism called hypocarbic bronchoconstriction, which could attempt to minimize ventilation to that unit and divert that ventilation to other normal alveoli. I have not read enough about it. The more popularly known corrective mechanism is hypoxic vasoconstriction, which would occur in that situation. The message therefore is that when total ventilation and total perfusion are normal, there still can be accentuated VQ mismatch in different regions of the lung during pathological states. An accentuated VQ mismatch would affect oxygen transfer and not carbon dioxide transfer. Because arterial PCO2 is normal in diffusion abnormalities under which we are classifying VQ mismatch, we already saw that diffusion impairment can occur when there is reduction in surface area of the diffusion membrane, increase in thickness of the membrane, and an accentuated VQ mismatch. We are equating VQ mismatch to loss of surface area. In VQ mismatch, which we consider as diffusion impairment, there is type 1 respiratory failure where arterial oxygen partial pressure is lower, but arterial PCO2 is normal. So, when do we worry about VQ ratio? When total ventilation is normal and total perfusion is normal, and we still see a reduction in oxygen transfer, that is when we consider a VQ mismatch. When total ventilation per se is less, that itself is a cause of respiratory failure. There will be type 2 respiratory failure in that case. When total perfusion is less, we have already seen that there is no abnormality in PO2 or PCO2 in arterial blood. When both these are within normal limits and there is still evidence of impaired gas exchange, that is when we consider the possibility of accentuated VQ mismatch in different regions of the lung. What are the consequences of hypoventilation, cardiac failure, and accentuated VQ mismatch? When ventilation is impaired, when there is hypoventilation, there is type 2 respiratory failure. So, in our mnemonic, we had that listed as V for ventilation impairment. When there is less perfusion, as in right heart failure, total oxygen transferred per minute is less, leading to tissue hypoxia. This was denoted as the S for the causes of tissue hypoxia listed here, stagnant hypoxia. However, arterial PO2 and PCO2 would be normal in this case. There is no arterial hypoxia. When there is VQ mismatch, what we have is something analogous to diffusion impairment, which is type 1 respiratory failure. Just to complete the picture, when total ventilation is more than required for a given metabolic state, arterial PCO2 would go down, leading to respiratory alkalosis. If this increase in ventilation is induced by hypoxia, that will be hypoxia. However, there are some cases where hyperventilation can occur in the absence of hypoxia, as in hysterical hyperventilation or metabolic acidosis. In these cases, there is not only hypocarbia, there can also be hyperoxia. We will now see some pathological causes where the VQ mismatch can be accentuated. If these are the alveoli and this represents pulmonary arteries and this pulmonary veins, then microemboli in pulmonary arteries, which prevents blood flow to certain alveolar units, will create alveolar dead space. We saw that already. In addition to these microemboli, which can create alveolar dead space, the other causes where perfusion in these capillaries can be hampered are when alveolar pressures are higher. If the alveolar pressure is high, it is going to compress upon the capillaries surrounding that alveolus, in that alveolar wall. If the alveolar pressure is high and there is compression of the capillaries, blood flow to those capillaries will be reduced, or there will be zero blood flow, what is called zone 1 pattern of perfusion. We will learn about the zones or patterns of perfusion later, but if you already know about this, zone 1 pattern of perfusion where alveolar pressures are higher, or when arterial pressures, pulmonary arterial pressures are lower, will result in alveolar dead space. Where can you have a high alveolar pressure? In chronic obstructive pulmonary diseases and in mechanical ventilation. The details we will consider later. So here we have three important causes for alveolar dead space: microemboli in pulmonary circulation, high alveolar pressures as would occur in COPD and in mechanical ventilation, low pulmonary arterial pressures as in right ventricular failure. When can you have physiological shunt? When there is blockade of the bronchioles, as would happen in a mucus plug in the bronchioles due to bronchiolitis or bronchitis, or alveolar collapse as in surfactant deficiency, which you will see in a condition called neonatal respiratory distress syndrome. Just remember these causes. We can learn the explanations in a later lecture. Thank you for your attention.